Suppose you have some pellets, and you want to group them by some kind of linking property, okay? Well, for these, obviously, you'd want to link them by color, so you'd make some buckets, a green bucket, a blue bucket, and a red bucket, and you start putting stuff in the corresponding color. You do this for a few, and then you just kind of do it for all of them. And you get a grouping of all your pellets into green pellets, blue pellets, and red pellets. Okay, cute, you've put pellets into colors, but how is this math, right? What am I trying to say here? Well, what we've just defined is known as an equivalence relation. What we've done is that we've managed to group things together based on a linking property that makes them equivalent, okay? Grouping is the relation, and equivalence is by the fact that these properties give a notion of sameness. So, what is an equivalence relation? Well, formally, it's a relation, and so this is a definition of a relation, which may seem a little pedantic and just uselessly formal. All this is saying is that it's some subset of a Cartesian product, which just means that formally it's a set with some pairs of elements inside it. And for a pair to be inside our relation just means that these two elements are related by our relation, okay? So in our case, if two pellets have the same color, we would have just put them as a pair inside our relation. For it to be an actual equivalence relation, it needs to satisfy these three properties. And this might seem particularly complicated, but all these properties are saying is, one, the property has to be reflexive. And reflexive is quite pedantic. It just means that an element is always related to itself. So in the case of our pellets, a pellet of a particular color has the same color as itself. And of course that makes sense, right? But we do have to include it because not all relations are reflexive. For example, the less than relation is not reflexive because x is not less than x itself. X is necessarily equal to x, so it can't be exactly less than. It can be less than or equal to. Next, we have a symmetric relation, symmetric property, which just says that if x is related to y, then y is related to x. Because note, we're looking at tuples here, and tuples do care about order. And so typically, the same relation here is not going to be symmetric, right? X is smaller than y does not imply that y is smaller than x. Okay? And typically I could have just taken equality, which is an equivalence relation. Well, equality is going to be symmetric because x equals y implies that y is equal to x. Alright? So this would be a symmetric relation. And then finally, we've got the transitivity, which looks the most complicated of all, but is again actually properly satisfied by the relation that hasn't satisfied what we had so far, which was the smaller than. If x is smaller than y and y is smaller than z, then you see immediately that x is smaller than z. Okay? That's something that you get immediately from that. And any relation that has this property, that if x is related to y and y is related to z, then x is related to z, is called transitive. So these are all properties you'd expect from something that implies equivalence. So for color, for example, the transitive relation would have been, if pellet A has the same color as pellet B, and pellet B is the same color as pellet C, then you'd expect that pellet A has the same color as pellet C. Okay? And symmetrics is the same, and reflexive is the same. These are all sort of basic properties you'd expect of something that defines an equivalence. And it turns out these are all the properties we really need to define what we mean by an equivalence. So let's look back to our pellets. Well, in the case of our pellets, we've got the set of x is going to be the set of our pellets, okay? And so now we're going to group them by color, and so that's the equivalence relation, it's color. Well, we say that a pellet is related to another pellet if they have the same color. And so then we group them into these buckets. But what are these buckets formally, right? I mean, we've talked about the relation, and we've talked about the actual elements of a set, but we haven't talked about actually grouping them together. Well, the set of all these groups is known as the quotient set, okay? And a quotient set is written as x mod or quotients, the relation. And basically the quotient is just the set of the groupings under our equivalence relation. And each of these groupings, so in our case our buckets, is called an equivalence class. So one way to think about the quotient set is as sort of like changing your lens and looking at things in a blurry manner. If you had really bad eyesight, right, and you looked back at this original set, and you looked at it with some really, really bad eyesight, then you might not be able to see any individual pellets. Maybe these guys would look a little bit blurred out, and you wouldn't really realize that there are two pellets. What you would be able to see, if you're not colorblind, is that there are exactly three colors within the set, right? You've got a green area, you've got some red patches, and you've got some blue patches, right? And so all the relevant information you'd be able to give with your blurry eyesight is that there are 3 colors within the set: green, red, and blue. And so this is exactly the type of information you'd get by just looking at the quotient sets. When you look just at the quotient set, you only get the information of the colors. You don't really get extra information about the pellets inside. You know, maybe these pellets aren't actually all round. Maybe there's triangular pellets and rectangular pellets. But right now all we care about is color. And so I don't know which ones are triangular and which ones are rectangular. All I know is that all these ones are green, all these ones are blue, and all these ones are red. And so it's a way of specifically focusing on a particular property and making things blurry according to that lens. And so quotients is really what I want to talk about in this video, not so much equivalence relations, because quotients are fundamentally important in math and specifically in algebra. And, well, that sort of brings us to our next question of who actually cares, right? Because we haven't really, formally we've been doing math with sets and everything, but it doesn't really feel like math. In math you like to see operations or geometry or something like that. Well, it turns out that in both of these cases, quotients do play a role. In geometry, things like, for example, the torus, the object, can be seen as a thing called a quotient space. And I'll be talking about this in, well, I possibly will be talking about this in a consequent video. What I want to talk in this video is about the case where we're caring about operations less so than geometric objects. And this may seem a little abstract, but hopefully you'll understand what this is saying by the end of this video. And so particularly what we're going to be studying is how you can use quotients to preserve operations and to sort of get a less complicated structure. We'll see what I mean by this. So first, to actually get how quotients act on these things, we have to sort of look at quotients under a different eye. So we've seen them as blurring things out, but what we're going to see them as now is as projections. And the way to see this is to actually look at a simple question, which is what is 30 divided by 5, okay? Straight away, this doesn't actually really have anything to do with quotients, but it's the idea of how we're going to think about this question that is going to bring about the idea of seeing quotients as a projection. So 30 divided by 5, well, you know that's equal to 6, right? You know that 30 divided by 6 is equal to 5. But one way to see both of these things together is to get a bunch of little circles, or I don't know, squares, or whatever you want, just a bunch of things, and you want exactly 30 things, and I've put 30 things here. And you group them in groups of 5, because you're dividing by 5. Or, as you can see, if I group them in groups of 6, then it's really the same thing. These are groups of 6, and these are groups of 5. And I can get the information of both 30 divided by 5 and 30 divided by 6 in this square. Because if I project to the right, well, not this square, this rectangle. If I project to the right, then I see that I get sort of 6 lines, right? If I get these lines here, and I project them onto single points, then I get 6 points. And so what I get as an answer is that 30 divided by 5 is 6. So 30 mod these groups of 5 gives us 6. And the other way around, 30 divided by 6 gives us 5. If I do 30 mod these groups of 6, I get a projection onto 5 points. Okay? So this may seem like a convoluted way to think about division, but it's going to be very useful for this next example, which is what are the integers divided by 5? Okay? Well, let's try and do the same thing. We'll group by 5. Now things are a little more complicated because we have infinitely many rows, so I can't really project to the right like I did before, because I just get another kind of infinite set on the right. And that's not really something we care about. So instead, we're going to do this sort of complement operation. Before a complement to 30 divided by 5 was sort of like 30 divided by 6. So even though I can't get the integers divided by 5 straight away, I can maybe get this sort of complement in the other direction of projection. And so I'm going to group these ones together, and I'm going to group these ones together, and I'm going to project upwards. Okay? And so let's give them a color to each group so that we can keep track of things a little easier. And so now we project them, and we're going to give numbers to each of our pellets that we projected onto. So 0, 1, 2, 3, 4. And one way to choose why we would have taken 0, 1, 2, 3, and 4 specifically is that since I'm working with integers, and maybe this pellet, which was the first pellet in our line, was 0, and maybe this one was 1, and this was 2, and this was 3, and this was 4. And note that was our first group of 5, and so then we continue, we get 5 here, and then 6 here, and 7 here, and so on. And so basically, when you look at it this way, what you see is that these equivalence classes, so these groupings, remember we called these equivalence classes, are really the set of elements that have the same remainder when you divide them by 5. So 0, 5, and then next we get 10. All of these have a remainder of 0 when you divide by 5. Then 1, 6, and then here we get 11. All of these have a remainder of 1 when you divide by 5. And all of these guys have a remainder of 2 when you divide by 5, and a 3, and a 4. And so really, we've managed to capture the notion of all the possible remainders you can get when you divide by 5 into 5 elements here. Okay? And so sure, it makes sense. The only remainders you can get by dividing by 5 is 0, 1, 2, 3, or 4. But what additional information can we sort of draw from the integers into this? Well, one of the basic things we do with the integers is we add them. Okay? And so we'd like to maybe add this new set of mod integers, which is the integers mod 5 is what they're called. We'd like to add them. So to add them, I'm going to dispose them on a circle. 0, 1, 2, 3, 4. And let's think about what I get when I add 0, when I add 1 to 0. Well, adding 1 to 0 just means adding 1 to all the elements that I have here. So I have 0, 5, 6, oh, not 6, 10, sorry, 15, and so on. Well, adding 1 to each of these is really just sliding each of these to the right, okay? I slide each of these to the right. So 0 goes to 1, and 5 goes to 6, 10 goes to 11, 15 goes to 16, and so on. And so what this tells us is that since adding 1 to each of the elements in this equivalence class gives me each of the elements in the next equivalence class, is that 0 plus 1 is equal to 1. Okay? But note that this addition here is not integer addition. This is really addition in our new number system of 5 elements. Okay? So that's to be expected, right? We'd like to have 0 plus 1 is 1, and we'd like to have 1 plus 1 is 2, and so on. Now the question is, what is 4 plus 1? Okay? Well, now when I slide, when I do 4 plus 1, what I'm sliding to is down to this next one here, because this is 5. And this one is 9, and 9 when you add 1 goes to 10, and so on. And, you know, this here I would have another pellet, which would be minus 1, and minus 1 would go to 0 when I add. And so we see that 4 plus 1 gets us back to the equivalence class of 0. This is why I put things in a circle, because things cycle back together. So if I look at each of the additions, they really correspond to rotations around my circle. You see I'm adding 3, I'm going towards 3, adding 4, going towards 4, but now that I'm adding 5, 0 goes back towards itself. And you could try and follow each of the points individually and see where they end up against each addition. So let's look at this a little more formally. What we've done is that we started with z, and z had an additive structure, and that's what we wanted to carry over, right? For it to have an additive structure just means that it's a group. I'm not going to go over the formal definition of a group, but a group, all it is just a set along with some operation, and you just kind of want the operation to be nice. So you get some nice properties like associativity. What you don't necessarily have is commutativity. So if my operation was a star, you don't necessarily have that a star b is equal to b star a. This is not necessarily true for every group. It is true in the group of integers for addition. Okay? When a group has the property, it's called abelian, and that's going to be important later. One of the main properties of a group, though, is that it has an identity, which if a group is G, the identity is EG. And in our case, EG is equal to 0, right, for the integers, because 0 plus A is equal to A. That's what it means to be an identity. To mean to be an identity is just that the identity operated with some other element just gives you the same element. The identity just does nothing under that operation. Okay? And the identity element is particularly important because it's the only element that's guaranteed to commute with other elements. You've got that 0 plus A is equal to A plus 0. And so in the case of integers, everything commutes anyways, but in our general group, EG star G is equal to EG star G, is equal to, erase that, is equal to G star EG, and all that is equal to G. Okay? So it's the only one that's guaranteed to commute, and we'll see in a second why that's important. And then in a group you have some other important properties like existence of an inverse, but we don't really bother with those. So, now that you've got an additive group, let's consider 5z, which is the subgroup of multiples of 5. So a subgroup is just a subset of the integers, which is also a group under the same operation. So it follows the same properties that the original operation had. In particular, it's stable under that operation, which just means that if I take any two elements of that set and I add them together, I still get an element of that set. So adding a multiple of 5, 5m, with another multiple of 5, 5n, gets you another multiple of 5. You just get 5 times m plus n. So it's stable under this operation of addition, and that's pretty much all you need to know that it's a subgroup. It's not. You also need to guarantee that your inverses are closed, but that's all we'll care about for now. So 5z is a subgroup. Now we write z mod 5z for the set of cosets of z, 5z. And cosets are just sets, not necessarily groups, where we just take all the elements of our set and then we just add a particular element to it. So for example, 1 plus 5z is just 1 plus the multiples of 5, which is exactly all the multiples of 5 plus 1, so all the elements that leave 1 when divided by 5 as a remainder. All these guys leave 2 as a remainder when divided by 5, and all these guys leave 3 as a remainder when divided by 5, and these guys leave 4 as a remainder when divided by 5. Okay? And so this idea of remainders brings us back to what we had earlier. And I could have written this one here as 0 plus 5z if you want. Okay? And note that these representations aren't unique, right? 2 plus 5z is the same as 7 plus 5z. And you can try doing that operation for yourself and seeing that these two sets are the same. And in fact, it's always going to be the same as long as this representative here has leaves a remainder of 2 when divided by 5. And so z mod 5z is the same as z mod our relation that we had earlier. And I didn't explicitly write out the relation. The relation was basically putting things together in an equivalence class if they left the same remainder upon division by 5. And that's exactly what we've done here. Okay? But z mod 5z also comes with a group structure, and it's the group structure we looked at before, where namely I could just add the representatives and then take division divide by 5 and take the remainder. So for example, if I added 1 plus 5z, okay, plus 4 plus 5z, and maybe I'll put a little circle on this plus to note that it's addition inside our quotient group. Well, that was just 1 plus 4 plus 5z, which was equal to 5 plus 5z, which is equal to 0 plus 5z, which is equal to 5z itself. Okay? So that's why we get this sort of new kind of cyclic operation. So we managed to get a group structure from z just by taking a subgroup of z and constructing this quotient group by using this sort of natural relation, where the relation is just saying that A is related to B if and only if A is in the same coset as B. So you said A plus, well, your subgroup, H, in our case it's 5z, is equal to B plus H, okay? If they're in the same coset. Okay, and so when a group that you quotient by gives you a group structure like this, you said that H is a normal subgroup. So when this relation here gives us the set of cosets and gives us an operation that's well defined, then you see that H is a normal subgroup. And let me say why this is subtle. Because we've defined operations specifically on the representatives. But how are we guaranteed that taking different representatives gives us the same results? In this case it is, right? If I take in 7 as a representative instead, then 7 plus 3 equals 10, and mod 5, that's just equal to 0, which is the same as 2 plus 3, which equals 5 is equal to 0, okay? But if I tried taking this with any kind of cosets for any kind of subgroup, then it might have not worked, okay? It works in the integers for every subgroup of the integers, but it doesn't work like this for any group. For an abelian group, you can take any subgroup, but for a non-commutative group, you don't necessarily always have that you can quotient like this. So being a normal subgroup is a very important feature. And here's another example, where if I take the real numbers and I quotient by z, z is a normal subgroup of real numbers under addition, you get the circle S1. So basically what I've done is I've sort of taken the real line and I've twisted it around. Maybe I can give some reference points here, where maybe all these points are 0, 1, 2, 3, 4. And I project, again, this idea of projection, I project them down onto a single point, 0 down here. And we see that if I add 1 to 0, then I go up in this direction, up to my thing, up till I reach 1, and I project back to the same thing. So it's sort of a continuous version of this cyclic group that we just got here, where we had 5 elements, and you could have done the same with z mod nz for any zn. But now we're doing it with r mod z, and it gives us a continuous version of this, which is the circle group. And so as an exercise, you can show, and it's an important exercise really, that the subgroup is normal if and only if g star h is equal to h star g for all g inside our original group. I should say for all g in G here. G. Okay? And why is this important? Because as I said before, the identity is the only element that's guaranteed to commute. So in a sense, the fact that a normal subgroup commutes with every element sort of tells us that it has the potential to be an identity, okay? And basically what we're doing when we're quotienting is that we're reducing things so that the quotient, the group you're quotienting by becomes the identity. In our case we had here, right, we had 0, 1, and so on, all the integers. Well, they got reduced to the identity for our circle, because when we added by this thing, then we didn't slide at all around our circle. Okay, so a bit more about groups and why quotient groups are important. Well, in the sense of group theory, why quotient groups can actually be important, is that groups, what interests us about them is not necessarily their elements, but their structure. And let's illustrate this with an example. Say I have two groups. One is the group of symmetries of the triangle, okay? And the other one is the group of permutations. So let me say what I mean by group on these cases. In both cases, what I'm taking is I'm taking an element of each group, and to multiply them, I'm going to compose them, which means I do one and then I do the other. So for a triangle, for example, a particular symmetry might be rotating by 120 degrees, and another symmetry might be flipping around this line here. Well, if I first rotate and then flip, that's like taking the product of flip times rotate, read-like function composition. Okay? And permutations is similar. You can take a permutation and then perform another permutation afterwards. So the notation here is just saying 1, 2, 3 here represents a permutation of sending 1 to 1, 2 to 2, and 3 to 3. And this one here represents taking 1 to 3, 2 to 2, and 3 to 1. Okay? And there's more compact notations, but here I've done it so you can see exactly where every element goes. Well, as a matter of fact, let's label the vertices of this triangle here, because really what is a symmetry of a triangle is just a sort of permutation of its vertices like this, such that the edges are preserved. And in the case of a triangle, this gives you a permutation group, because if I rotate, for example, by 120 degrees, you'll see that 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1, which is exactly the same as this permutation we have here. 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1. Okay? And if I'd taken flipping instead, well, 3 gets sent to 1, and 1 gets sent to 3. And that would have been the same as this one here. 1 getting sent to 3, and 3 getting sent to 1, and 2 just not moving at all. And so it's not just enough to say that we can get this sort of like identification between elements on both sides, because if they're the same size, you can sort of get an arbitrary identification, because, again, intuition isn't necessarily formalized in mathematics. But what's important is that the operations are preserved as well. Namely, if I first apply this permutation, and then apply this permutation here, it turns out that what I end up getting as a permutation is first I take 1 to 2 and then 2 to 2. Okay, so 1 goes to 2. Then I take 2 to 3 and 3 back to 1, so 2 goes to 1. And I take 3 to 1 and 1 back to 3, so 3 stays fixed. So what I get is I get this permutation here. And so translating this to a triangle, that means that, again, if I label things, if I take first the rotation and then the flip, then what I'm getting is just the flip alongside here. Or I get 1 to 2 and then 2 to 1. And you can check that if I first wrote it in this direction and then flip things, it's the exact same thing as if it only flipped in this direction. And this is true for all the operations you can take. So for these groups, it's sensible to say they're the same. And to say that, you say they're isomorphic. Formally, to be isomorphic means you have a map between your two groups such that the map preserves operation. Okay, so this map is called phi. And basically, phi of any particular operation in our first group is just the phi of the elements with the operation in our second group. Okay, so in our case, phi, which was the map of identification we used here, of the rotation times the flip, just gives us phi of the rotation, which was this, times phi of a flip, which was this. And that gave us this, okay? And it was the same as the results of first doing the rotation and then the flip and then taking the phi. And so we want a map like this to be between our two sets, and we want that map to be bijective, which just means that we managed to get an identification like we did before, so that every element in our original group has an equivalent in our other group. And by this equivalence, you still preserve multiplication. But saying that you want to have an equivalent for every element of both groups is a little strong, and it says that you have an isomorphism between the two groups. But a little bit of a weaker statement is to say that there's a homomorphism from one group to the other, which just says that you can take every element in one group, so maybe a homomorphism from here to here. I can take every element in one group, and I can sort of send it to another element in the next group, such that this operation is preserved, right? And now it doesn't need to be bijective. It can be injective or surjective or none of those, as long as it just satisfies that it preserves operation. And so what you're doing in that sense is that you're just reducing the group to a sort of smaller group that sort of blurs out the original subtlety of the operations you had before. And that you preserve the operation, but some of the elements might get mapped to the same elements, okay? And so once again, this idea of blurring out should evoke the idea of a quotient that we did earlier. And the way this is related to a quotient is via the kernel. The kernel of phi is just a subgroup, well, it's just a set, where every element of a kernel is every element of our original group that gets sent to the identity of our second group. So in our case, because we had an isomorphism, well, what got sent to the identity in our permutation group was the identity in our original group. The identity in our original group is just the symmetry of doing nothing. And the identity in our second group is just the permutation of doing nothing. And so those got mapped to each other. But in in a homomorphism, which is not necessarily an isomorphism, you might get elements that get sent to multiple elements that get sent to an identity. And as it turns out, this set of elements is a normal subgroup of our original group, which means we can quotients by it and get an addition property kind of thing. And again, this idea that the set is the set of all elements that gets sent to an identity in our new group should call back to what I said as an exercise, which I said that the normal subgroup had the potential to be an identity. Well, it's exactly what it's saying here, because in fact, every normal subgroup is the kernel of a homomorphism. So having the potential to be an identity means you can make that group an identity through a homomorphism, and then get a sort of simpler group, which is the homomorphic image of that group. And so that leads us to the next theorem, which is the first isomorphism theorem, and it really should be called the fundamental theorem of abstract algebra, I guess, in my opinion, because what it's saying is that quotienting by the kernel gives you the image. And so let's look at a visual example of this, and it's particularly relevant to linear algebra. Let's say you're projecting vectors along this line here. Well, if you're projecting vectors along this line, then every element on this line will get projected to the origin. And every other element will get projected to some element on this normal plane. And so, in linear algebra terms, this line is the null space, and this plane is the column space. And so what we've just said is that our original vector space, quotiented by the null space, gets us our column space. It's a little more subtle than that because we're dealing with vector spaces and not groups, but you get the rank plus nullity theorem, which tells you that the dimension of a null space plus the dimension of the column space gets you the dimension of your original space. In this case, 1 plus 2 equals 3, right? And so again, this maps together, well, this sort of links together the idea of a projection and the idea of a normal subgroup being like an identity. Because here we're projecting along a direction, and every element that was sort of defining our sense of projection gets mapped to an identity. So it had the potential to be an identity, and it becomes an identity. Okay. A more abstract example is really relevant to just group theory, and I sort of guess you'll just get it if you see it, and if you know about it. But this is basically talking about the idea of a free group and of a presentation for a group. And maybe I'll talk about this in more detail in some other video. It's truly interesting. So that's why we care about quotient groups, and specifically in the sense of algebra. And so now, we've seen that quotient groups and normal subgroups sort of give us a microscope framework, where now we can study groups alongside this microscope, where if I have a group, like this, right? And I have some normal subgroup inside it, or just a regular subgroup. There's two things I can do now. I can zoom into this normal subgroup, or this subgroup. I can just zoom into the subgroup and get information locally about what's going on around here. But that might not capture information about what's going on outside of it. In the case when it's a normal subgroup, though, not only can I zoom into it, but I can also blur things so that this sort of whole patch becomes a single sort of point that you can distinguish as a single piece of a resolution. And so now, by blurring alongside, well, relative to this normal subgroup, you get a blurry image of your group, but keeps some of its structure. It's a homomorphic image of our group, specifically by what we said earlier, by the first isomorphism theorem. So it keeps some of the structure of our original group, but not all of it, not all the details. But at least by looking at different normal subgroups, you can sort of get different kinds of resolutions of our original group and hopefully gain enough information to know everything you want to know about your original group. So that's why quotient groups are so important. And so now you might ask, okay, well, can every group be blurred out like this? Can you make a blurry image of every group? Can you lower the resolution of the image of every group? Answer is no, you can't, because some groups are called simple groups. And simple groups are so simple in a sense that they don't have any normal subgroups. So you can't you can't change the resolution. They're as detailed as they can be, and you can't lower the detail anymore. They're that simple. Except simple is a little misleading because they're really not that simple. Here's one infinite family of simple groups. It's the prime cyclic groups, and we've looked at cyclic groups before. We looked specifically at Z mod 5Z, and if we just generalized our clock arithmetic that we had before to any n, then we'd have seen the general cyclic group, and specifically when you take n to be a prime, then you get a simple group. And that sort of makes sense, right? Because primes also have this sort of property that you can't reduce them any further, just like simple groups do. So it makes sense that you have some kind of relation to the primes. So this is an infinite family of simple groups, and it's the most simple one. Then you get the alternating groups, which are already a little more complicated, and I'm not going to talk about them here, but they have to do with permutation groups, the ones that we saw before, which are groups of permutations. But alternating group is specifically the group of so-called even permutations. And the fact that these are simple for n bigger or equal to 5 is closely related to the so-called insolubility of a quintic, which you may have heard about, which says that every quintic polynomial, well, no quintic polynomial, or there's no formula to solve them by radicals. And not just quintic, it's true for the sextic, for the heptic, and going on for n bigger or equal to 5. That's closely related to the fact that an is simple for these values. Then you get all this mess here, which isn't actually really a mess. It's all, these are called groups of Lie type, and then you sometimes get further classifications where you look at Chevalier groups, or you look at Rie groups, or things like that. And these also define, some of them define infinite families, some of them are sort of singled out, like the Tits group here. And they look like a mess right now, especially because, well, their constructions can be quite convoluted. But there is a structure to them, and there's a relation to other aspects of algebra that you can see in these. So they're still, in some sense, simple. They're not actually simple, but there's a structure to them. So it may feel a little bit disheartening to see all of these, but it still gives us a sort of nice classification for our finite simple groups. If we were done here, but we're not. Then we had these 26 so-called sporadic groups. And sporadic because they're not in any way related to the ones above, and they sort of stand out on their own. So you've got this subset here of, I included this one, of so-called Mathieu groups. You've got Conway groups here, you've got Fisher groups here, and then you've got this odd lad here called the monster group. And the monster group is special. First of all, it has this border here. This means that this is the size of a monster group, and I can't say this number right now, it'll take too long. There's also the baby monster right here. And the monster group is particularly interesting because in some sense it a lot of these other sporadic groups sort of come as subgroups or quotient groups of the monster group. And so this here gives us a complete classification of every finite simple groups, and the proof of all this was done over many years by brilliant minds in about 10,000 pages. So it's really quite a complex proof, and it brought up a whole lot of philosophical debates about what we actually want things to be a proof or not. And the monster group is particularly special, and people are still sort of wondering about where the monster group comes from. It's sort of a mystery, right? I mean, why would something so big be so simple, in a sense? Well, it's still a mystery to be solved. And as a matter of fact, the monster group does arise as a sort of, as a symmetry, well, more or less a symmetry of an object living in a 196,883 dimensional space. And we've found actually a bunch of connections between the monster group and number theory via a very special function called the J-modular function. But I won't get into that at all. Not just because I don't have time, but also because I don't quite get all of it myself. So hopefully that's got you a little bit hyped for the idea of group theory, and I might do more videos in the future on specifically finite simple groups. So stay tuned for those if I make them. And see you then.